Let's take a look at conservation of energy. Now, conservation of energy can be represented by a COE. It's a law or a principle which states that energy cannot be created or destroyed. It can only change its forms, or it can be transferred to other forms of energy. Now, the main idea is that since energy cannot be created or destroyed, it means that you are not going to change the energy. It's going to stay the same. It's a big idea. Just like mass, you cannot create a mass or destroy it, but you can only make the object move or the mass move. Other quantities that we have seen before are force, acceleration, velocity, and displacement. All of these are not conserved. What it means is that you can change the force, you can push or pull an object, you can change the acceleration, you can change the velocity, or you can even change the displacement. But the energy is conserved or remains the same. Now, if we are talking about the system, it can be defined as the collection of objects that we define in a scenario. Now, what I mean by it is it can be one object, like let's say we have a car. It can be two objects, a person and a car, or it can be many objects. For this scenario, we can take a person and a car and also include the Earth in the system. There are many other examples. So any objects that we decide to group together, we can call that as a system. As we have seen before, a person pushing a car is one system, and we call that as open system, whereas the person sitting inside the car, we call that as a person inside the car as one system, as a closed system. So let me define again what a closed system is. So the person sitting inside the car and accelerating the car, where there's no work done on the system from the outside, or there's no external work done on the system, in that case, the energy of the system remains the same because you cannot create energy or destroy the energy. And according to this law, or according to this statement, we say that the initial energy or the energy at the start is equal to the total energy at the end. So whatever energy the person has while accelerating the car is not going to change, or the change in the energy is going to be zero. And that's one statement for conservation of energy when we are considering closed system. Now, when we take a look at a scenario with open system, which means that there's some work done on the system from the outside or an external work, it's the same example that we had before of a person pushing the car to make it move. Now, if you look at the system in the box, there has to be some external work done on the system in order to change its energy. So according to this statement, or an open system, the beginning energy or energy at start, adding some work to it or external work will equal the energy at the end or after the work has been done on the system. So if we rearrange this equation and move the initial energy to the other side, we get the equation of work is equal to delta E, which we've already seen as the work energy principle, or also of a falling object. Now let's take a look at an example of a falling object. Let's say we have a box which starts at rest, and it's initially at a height of h, and when it falls it reaches its end point, which is close to the ground, and we're trying to find how fast the object is moving at this point. Now to answer this problem, how fast is the object moving, we can use the kinematic equations, but that's a long way to solve this problem. We can use the energy conservation and figure out the energies at the start point and the ending position. At the potential energy, it's not moving, so no kinetic energy. At the end, it's moving, it has some velocity, but it has reached the ground, so we'll ignore the gravitational potential energy because it's zero and write down the kinetic energy. So let's start with considering it as a closed system. What it means is that we are saying that no external work is being done by the Earth and the box is moving on its own. It's changing its energy from gravitational potential energy to all kinetic energy. When you plug in the equations and solve for the velocity that you're looking for, I'm going to use the symbols I and F for start and end, and then cross out the mass and solve for the V by moving the half to the other side of the equation, and then you need to take the square root as well because that's Vf squared equal to 2gi hi. Now hi is the height at which the object is placed, and it's the initial height at which the object is starting to move to get the final velocity. That's all we need to solve for it. Now if we consider it as an open system, we're going to say that there's some work done by the Earth, and since Earth is not in the system, we are going to consider the gravitational potential energy at the starting point equal to 0, and all the work is done by the gravitational force. So if there's no energy, which means that being at rest, no kinetic energy, no gravitational potential energy, in that case we only need to figure out the work done from the Earth. The force is Fg, height is the displacement, and cosine angle is 0 because the force and the displacement are both in the same direction. So we end up with FGH, and I'm replacing the Fg with mg as we have seen before for gravitational force. Now let's look at the energy at the end. Since it's moving, again, Earth is not part of the system, so there's no gravitational potential energy, and final energy is half mv squared. So now when we put these two sides together, it's similar to what we saw in the closed system, the same equation, and we'll solve to get the same equation for the final velocity. Each other, it's pretty much the same equation that you saw in the closed system, and it will drive you the same final speed. So if you look at this type of example, it doesn't matter whether you take it as a closed system or an open system, the answer is always going to be the same. So we'll get the same results. Let's take a look at another example. This time we have an object on a ramp and it's been pushed with some velocity. It's moving with some velocity, 5 meters per second, and it stops eventually at some height on the ramp, and we're trying to figure out how much height did it reach on the ramp. Now if you look at the system, there's no energy or work done by the ramp, so we'll not consider this as part of the system. We'll only look at the box and consider it as a closed system. So the start energy at the starting point, since it's moving, it will have some kinetic energy. At the bottom, since it's no height, so gravitational potential energy is 0. At the end, where it has the final energy, it stops, so there's no kinetic energy. And since it has reached some height, so it's going to have some gravitational potential energy. So now when we use the closed system, we plug in the equations for kinetic energy for the start or the beginning energy, and gravitational potential energy for the final energy at the end. And we can put these two sides together and solve for the height. I'm going to replace the initial velocity with vi because that's the velocity in the beginning. We can cross off the masses because there's same terms, and solve for the height as 1.28 meters. Let's take a look at another example. This time we're moving the object on a surface, and let's say it starts from rest. It has some mass of 10 kilograms and is being pushed with some force to the right, and we're trying to find out the velocity or the speed at the new position. Let's say there's some work done by the force, and that's equal to 150 joules. Since there's some work done by an external force, we can consider it as open system. So we'll take the equation for the open system, identify the energy in the beginning. Since it's at rest, no kinetic energy, no height, so no gravitational potential energy either. Plus the work done is 150 is equal to half mvf squared, or the kinetic energy at the end point. Now since I said it's 0, so I'm going to cross it off and solve the equation for Vf, and I'm going to get the velocity as 5.48 meters per second. Let's take a look at another example of a projectile thrown from a height of 50 meters, and it is being horizontally launched with a velocity of 30 meters per second. We're trying to find out how fast is the projectile moving at a height of 20 meters. Now we can take this as a closed system and do not consider the work done by the Earth. So we can take the first position as a start and the ending position where it is at a 20 meters height. Since it's moving in the beginning, there's some kinetic energy, there is some height as well, so there's some gravitational potential energy as well. So I'm going to use the kinetic energy and gravitational potential energy equations as my start or beginning energy, because it's moving with some velocity and some potential energy. Since m is a common term, so I'm going to cancel those out and rewrite my equation, simplify my equation before plugging in the numbers. So after I've simplified the equation, I'm going to plug in all the numbers that I have from this given problem. Since I do not know the final speed or how fast the object is moving, I'm going to leave it as Vf in the equation. When I solve, multiply the numbers and square the numbers that need to be squared and add them on the left hand side, I will be able to simplify this equation to solve for the final speed. To get rid of the 196 from the right hand side, so the final speed or final velocity after you take the square root will come out as 38.6 meters per second. Let's take a look at a last example. Let's say we have a book and it's on a table and it's moving with some velocity 3 meters per second to the right, and let's say the surface of the table is going to resist its motion and eventually it's going to stop at a new position, and we're trying to find out how far did it. So let me draw the friction force on towards the left resisting the motion of the book. And let's say we have some friction force which is 10 newtons, and we're trying to solve for the displacement or the S. Now let's take it as an open system because friction is doing its work. So we'll take the initial energy, beginning energy, plus the work and find the final energy of the system. Since it's all placed on the table on the same surface, no height involved, so there's no gravitational potential energy, and the work done can be calculated by using the friction force as the force doing its work on the book. Now they're in opposite direction to the displacement, so I will take the angle as 180 degrees, and cosine of 180 degrees is -1, and plugging in the numbers that I know, I get -10s as the work done on the book. The beginning energy, it's moving, so it's going to have some kinetic energy, and when I use the equation for kinetic energy, I get the answer 9. As the final energy, there's no kinetic energy because the object is not moving, no gravitational potential energy, same level. So all I have to do is 9 minus 10s equal to 0 and solve for the displacement, which is 0.9 meters to the right.